Hi, I'm Guang 115 years old, secondary 3 from Ennis High School. In this lesson, we're continuing with the techniques of definite integral. So, for this lesson of techniques of definite integral, we will be taking a look at this example that we have over here. So in this example, we're taking a look at the cardioid r is equal to 1 plus cosine theta. Now this doesn't seem like the normal kind of equation that you would get, since this here is in polar coordinates, whereas normally your x and y, or even with z, there would be your Cartesian coordinates or rectangular coordinates. So in this case, with your polar coordinates, you have to be aware theta being your angle, r being your radius, you could say that. So since we're given this cardioid, we need to find the perimeter of this cardioid and the area bounded by the cardioid. So firstly, what is the cardioid? So that would be something that looks like a heart shape. So of course, if you want to try to see what this graph exactly looks like, you could go to like apps that can graph for you, or if you have one of your own, you could use a graphing calculator to find it. So you just have to be aware this is in polar coordinates. That means you have to be aware your graph should be in polar coordinates unless you know how to use the parametric equations. But that will be another story, which you can convert to it, of course. So with this polar, or this equation in polar coordinates, this will be around what it looks like. Alright, so for this part, what you would see is that heart shape with its two parts pointing towards the left. So now let's take a look at what it looks like if we just roughly sketch it out. Alright, so let's say this is your x-axis, and this is your y-axis. So here would be your origin, and let's say the heart intersects the y-axis at these 2 points and the x-axis at 2, if you know how to calculate it. So this would be what the cardioid looks like. Alright, so for this cardioid, of course this is an enclosed area, so that means there is a perimeter and there is an area bounded by it. Now let's start with the perimeter. How do we find its perimeter? Right, so first things first, let's take for example this line over here. Of course this is more of an exaggeration and all, but so in order to find a perimeter, you would need to know, let's say, how long is this section over here, right? So let's just say we take this section as an example. So in order to find what this is, let's say we have it, like we just make it very obvious, alright? So you can make it so obvious that you literally have, let's say, dx and dl or dy, whatever you like, alright? So what would this exactly be like? Now of course you could have it look like a triangle. Well, here's what happens to make it look like a triangle. Well, if you think about it, you have learned about it, you could use a Pythagoras theorem over here with x and y to find dl. But now the problem is, how do we find x or y? So in order to find either this so-called dx or dy, we're not exactly going to change that equation into parametric equations and find it all. No, we're not going to. But instead, we're just going to keep it polar coordinate for now. So how exactly do we find it in polar coordinates? Now, in order to find this little piece, whoops. So let's say we're trying to find dl. So you could say this is dx squared plus dy squared. But how about let's think about it in polar coordinates. So let's say we have, now this is just from your origin a little piece extending outwards, alright? So that is your dr. So what if you have this dr? What would the other part be? Now this other part, if you can think about it, so we want a little section of this part. If we want a little section of that part, how about we use r d theta? Now you might be wondering, what is r d theta? This r d theta is, so r, which is your length, d theta would be that little angle you have. So this part here would be the little arc that you will see, right? So for these two parts, they're going to be perpendicular to each other. That means you could use this to use your Pythagoras theorem and to find your little length over here, alright? So how about let's use this part. Now that means your perimeter is going to be integrate from something to something, square root dr squared plus r d theta squared, alright? But now what is its boundaries? So let's think about it. So if you already found it, then good for you. So since we have this origin, then that means you'll have from 0, you can say this is 0, pi, half pi, and then pi, then 3 pi over 2, 2 pi, or 0, and then negative half pi, negative pi, and all, alright? Now, which order would we prefer? So let's just say we use negative pi to pi direction, alright? Alright, so when we take a look at this direction, you might be wondering again, how do we solve this? It doesn't seem possible, does it? Well, there would be a little trick to this, which is you can kind of think of it as you are just taking out a d theta. Alright, so this is what happens when you kind of take out the d theta. Now, dr d theta, we just have to differentiate this part. Well, 1 is 0, cosine theta becomes negative sine theta. But then, since this is squared, so it is just sine square theta. Now back here, we have an r square. R square, we just directly put this inside. 1 plus cosine theta, and then squared. Right. So what's so special about this part? Now how about let's expand it. You're going to have 1 plus 2 cosine theta plus cosine square theta. Sine square theta plus cosine square theta is going to be 1. So we're going to have 2 plus 2 cosine theta, alright? So how about let's remove a square root 2. And we're going to see 1 plus cosine theta d theta. So then again, you might be wondering, wait, how do we solve this part? So this part here, if you know how to solve it, you could use a half angle formula, alright? So if you forgot what the half angle formula is, of course you could derive it again from the double angle formulas. So let's take a look at what we are going to see. Right, so this is what you're going to get. Well, you have now a 2, since there'll be a square root 2 that comes out. Then integrate from negative pi to pi, and then cosine theta over 2 d theta. So now we can actually pretty much just integrate it already. Since this is a theta over 2, that means you'll need over 2, where you have to multiply it by another 2. So you have 4 sine theta over 2. And this part over here, you have to substitute negative pi and pi. Now, what do you get for sine pi over 2? You get 1. What do you get for sine negative pi over 2? You get negative 1. So 1 minus negative 1 will be a 2, which means you get 8. Alright, so it will be 8 watts for your perimeter. Well, of course, you could say that this is just 8 units, alright? Since in this part here, we don't exactly have the kind of unit, but we would just have, like, let's say 8 units of length for your perimeter of the cardioid. Alright, next up, we need to find the area bounded by this cardioid. So how do we find the area? Now, for this area, it could be kind of more easier to think about than your perimeter. So now if you go by a similar thought process where you just have one piece of it, one slice of it, so let's say you take out this slice over here. Now what are you going to have? So what you're going to see would be, this is a sector. Well, you can think of it as a sector at least. So here is an R, your R. Then, of course, here is d theta. Now that means this part will be r d theta. So then you could just use the method to find your area of a sector to find it, which you'll have half multiplied by r multiplied by your length over here, r d theta. Alright? So that will be a half r squared d theta already, and which is when we could start integrating it. Alright? So now I'll just be erasing this part to write the workings. Alright, so now we'll be taking a look at the area bounded by this cardioid. So as what we have said just now, yes, we would go by the kind of sector area. Alright? So this area would be equal to, so it's either you put half integrate r squared d theta, but this now has to be from something to something that includes the entire round of it. Alright? Or if you don't want to include the entire round, just half of it, you could just use times 2, which removes this half. Of course, you can't just use a quarter since only symmetrical about the x-axis, not the y-axis. Alright? So if you want to use half, you could use, like, let's say 0 to 2 pi, or negative pi to pi, whatever you like. Alright? Or even if you want to go for a challenge, like let's say pi over 3 to whatever, you can calculate it by yourself. So you just have to be aware it has to be in the anti-clockwise direction, since that is the direction where you have your theta that is increasing. Alright? So anti-clockwise direction, always. Well, if you want to go in the other direction, up to you, but you have to be aware there will be a negative since it is going the opposite direction. And same thing applies to, let's say you have x and y axis and you have a random curve, let's say. So A, B. You also integrate from A to B, not the other way around. So in this case, the positive direction for theta would be anti-clockwise. Alright? Okay. So this will be what you see. Or even if you have negative and all, then those you just kind of try to calculate it in with whatever signs you have, right? Or even if you want to go like pi to 3 pi or something, I don't know. Right. So this is how we'll find the area. Now R, what is R again? R is 1 plus cosine theta. So we just plug that inside. So what is so special about this puddle here? How about let's expand it? Okay, so this is how it looks when you expand it. 1, okay, we can integrate it. Cosine, yes, we can integrate it. Cosine square, how do we integrate that? Well, we would use the double angle formula. And what would that leave us with? So 1 plus 2 cosine theta. Now, if you can recall your double angle formula, then this would just be cosine 2 theta plus 1 over 2. And then here, the theta. Alright? So from this part, what you see, then how about let's just rearrange it a little bit, or you can also just directly integrate it, since you would have a 3 over 2. So let's put this half out here again. So 3 over 2, you just get 3 over 2 theta. Now this part, 2 cosine theta, it would give you plus 2 sine theta. Is that right? Alright. So then for this part over here, where you have a cosine 2 theta over 2. So cosine 2 theta over 2, that means you have sine 2 theta over 4. And this entire part, you have to substitute theta with 0 and 2 pi. Right, so this is all that you have to find now. For this first part, you are going to have, so 3 over 4 times 2 pi, which will have 3 pi over 2, minus 3 over 4 times 0, which is 0. So sine 2 pi is 0, sine 0 is 0, sine 4 pi is 0, sine 0 is 0. So that means this is what you're going to have, 3 pi over 2. And if you want to include unit, then this will be unit squared. Alright? So this will be the area bounded by your cardioid. Now that we have solved for both your perimeter and your area bounded by this cardioid, with similar thoughts actually, since in your perimeter you have your Pythagoras theorem in order to find the little length, and then have your angle in your anti-clockwise direction, which is negative pi to pi. Alright, so negative pi to pi. Alright, and then afterwards you just make a few simplifications using a half angle formula, integrate it to get your perimeter. Well, for your area, it's just a bit different. Well, you could say it is pretty much an integrand difference. So in this case, since it is area, you're just using the area of your sector, and then you add them up little by little in your anti-clockwise direction. And then you integrate it using double angle formula and just your basic formulas for integration, and you get your final answer. Alright, so that is pretty much it for this lesson on the r equals 1 plus cosine theta cardioid. Now of course, if you want, you can go ahead and mess around with it, like whether positive or negative one, positive or negative cosine, or sine or cosine, whatever. You can go and experiment around with it on your own. So for this lesson, I'll just be ending it here, and thank you for your watching.